So, uh, good evening, everyone. I'm Chaitanya Mandala. I'm a graduate student studying in University of Sapienza. I've done space studies program in Netherlands by International Space University, and my interests are guidance and navigation and telecommunications predominantly. And during free times, I also teach math and physics to high school students. Today, what I want to share with you is one of the projects that I've been working on, which is optically tracking satellites by using FreeFlyer. So many of the satellites are tracked using radio observables, but in our university we do that using optically tracking optically, which is done by a couple of telescopes that our university owns. And we start this process by using initial prediction that is done by NORAD, and they release what you call is a two-line element, a set of data that is released for each of the observed satellite or debris that is floating around in space. So the two-line element has this particular standardized format that has a unique identifier that identifies each of the space object, but it also has the orbital parameters that you can see here. Okay, so these two-line elements are used in coordination with SGP4 or STP4 propagators, and the two-line elements are specifically built to work along with these SGP4 parameters. So even though there are other parameters, these are the best. These work in best with coordination. Okay, these work in best while working together. The prediction accuracy is very important when you're taking an observation. And for the two-line elements, the position accuracy is 10 kilometers, which means that if you say the satellite is at 450 kilometers, you know that with a certainty of plus or minus 10 kilometers, which is not great, but you can use the data to improve that. You can use certain observations to improve that accuracy. And velocity accuracy is within 0.1 to 0.01 kilometers per second. All right, so for taking the observations using a telescope, what we do or what we use is two parameters called right ascension and declination. The right ascension and declination are taken in an initial reference frame, and the red line that you see here represents the right ascension, and the green line represents the declination. So say you're standing on the terrace facing towards the north, and if you turn around in the same place that you're standing, without changing your eye level, you're changing your right ascension. While if you move your head up and down to locate any point in the sky, that is you changing your declination. And by changing just these two parameters, we can visually point out at any particular point in the night sky. And this is what the telescopes do as well. So they combine right ascension and declination to point out at any specific point in the night sky. So what we'd like to do is to first identify what sort of satellites are visible from for the telescope during a certain period. And after deciding that, we have to exactly locate at what time the satellite would be visible at which point. So this is a video simulation of exactly that. So as you can see, the yellow lines point out different satellites, but the green ones point out when the satellite is visible from the ground station. So this is a way to predict when the satellite is visible at what time. And at the next level, we'll see how to also predict the right ascension and declination for the telescope to use that. And this is done in FreeFlyer. All right, Sapienza's telescope facilities, there are two two telescopes. One is based on Rome and the other one is based in Colorado. These are both remotely operated telescopes that we usually operate from the laboratory. And these are the specific coordinates that we use in the codes to predict the visibility. So the procedure for measuring, or the procedure for predicting this visibility is as follows. So first we read the initial position or the initial prediction of the TLE released by the NORAD, and we then convert that to position and velocity vectors, which act as an input to SGP4. And this is all done in MATLAB. All the steps are done in MATLAB. So after getting the position and velocity vector in SGP4, the output is in a format called TEME. This format is converted to ECI, which represents Earth-centered initial reference frame. And after the Earth-centered initial frame, it's converted into right association and declination to check the visibility from the ground station. Once we know that the satellite is visible from the ground station, we use right ascension and declination to convert it into local reference frame. And here is where we use the Earth orientation parameters. So while moving from initial frame to a local frame, we have to account for the movement of the rotation of the Earth that we have seen in the video earlier. So how does Earth move? It's obvious that Earth, there is rotation, but there are subtle movements that are not directly visible that change every day. And these are caused by precession and nutation, which are precisely measured and released in the form of polar motion, of which the data is available online. So we use the Earth orientation parameters of the day that we run the code to precisely convert from Earth-centered reference frame, Earth-centered initial frame, to a local reference frame. Once we have the right ascension and declination, we take the observations, and this is what the observations look like. But I'll come back to this in a few minutes. So we did the entire code in MATLAB. We were a team of 4, and it took 6 weeks of working together, developing and troubleshooting all the code to make sure all the moving parts are working well together. FreeFlyer has tools that do a lot of this job in a very reliable and very quick way. So FreeFlyer, so all the steps can be done using these codes. So using a load TLE method, we can directly load the TLE for all the satellites that we want to observe, and we can define ground station parameters like this. You see there's ground station parameters for Rome and Colorado. Checking visibility is done by visibility calculator tool. So this object is very useful because it gives you ability to measure the visibility from different objects like spacecraft or ground station or a moving vehicle to another spacecraft, or so you can measure the visibility between spacecrafts or ground station and a spacecraft. So there's a lot of flexibility with the visibility calculator here. So the observations were taken by remotely operated telescopes, as I said the other day. As I said a few minutes ago. But to avoid the trees or tall buildings or low-hanging clouds, we made sure that the declination was at least 20 degrees. So even if there are a few satellites that were visible below the 20 degrees, we choose not to point the telescope at them. So the algorithm was successful for at least 60% of the time, because as we've seen, the TLE has an inbuilt error based on the measurement type, or just because the time has passed from the from the generation of TLE. So not all TLEs are released in a consistent manner. It depends on what type of satellite it is. So few satellites, for example, a geostationary satellite would not change its position very frequently, right? So for those geostationary satellites, the TLE is released for a week with a frequency of a week, while LEO satellites undergo variations very quickly due to exposure of drag and other effects that the satellite has to go through. In this case, the observations are released every few tens of hours, every 15 hours or so, or based on any anomaly. So it depends on exactly on which satellite you're looking at. The updating of the TLE depends on that. So because of this variation, you could also see that the errors are propagated between the TLE generation and the observation time. So the image, this is an image that is taken from the telescope initially, and the streak of line that you see here is the satellite. And so depending on which orbit the satellite is, will decide how much time we would like to expose the telescope to the satellite. So in the LEO satellites, it's 2 or 3 seconds, for example. And so once we've taken the observations, we upload them to, we use a website called astrometry.net, which automatically identifies what stars is the satellite in presence of. So it identifies all the all the stars that are identifiable, and recognizes which part of sky we are looking at. And based on that, it assigns a right ascension and declination to each of the pixel that you see on the right image. And in using that calibrated image, we can calculate the right ascension and declination of the satellite at the observation epoch. And what we'd love to see from FreeFlyer in future is a way to export the text file that is generated from the right ascension and declination that we could directly use with the telescope software. So this is the format that we use for the telescope. So the command slew to RADDEC is telling the telescope to move to that right ascension and declination and wait until a certain time and take a number of images. So it's taking 2 images here, but just by changing this part of code, we can select how many images we can ask the telescope to take. So if FreeFlyer can automate this process, that'd be awesome, and it'd be very beneficial for many universities that also use telescopes. Not only universities, but other users of telescope in general. Conclusion and the use of optical observations. We initially tried to work with MATLAB, which took a lot of time to get the code working and predict the right observations. But with FreeFlyer, it could be done in a very short time, and it could be used to predict the local position of the satellite. And so for the students who are attending the webinar here, the FreeFlyer can also be used in coordination with your coursework. So if you're taking a guidance and navigation course, like I am at the university right now, I try to model the effect of the Earth not being exactly a sphere, right? So it's the J2, which is the main which is the main part of it. The orbit changes exactly like this. So the orbit is undergoing precision with a particular time period. And the time period, if you try to run different simulations, you would see that it would increase as the semi-major axis increases. But also there are very different, and there are also other parameters that affect this precision time period. And this is a combined effect of J20 and multibody effects, which imply the effects of sun and moon on an orbit, right? So this is simulated for a MEO satellite, and as you can see, it combines two different effects, giving a peculiar rotation to the orbit itself. The one you see in the red is undergoing the J20 and multibody. The one you see, the orbit that you see in blue, is taken as a reference to be able to compare how the orbit change is happening. All right, so the next one, I've made a plot using FreeFlyer to compare right ascension of ascending node with respect to time for a geostationary satellite. So I propagated this for 65 years. So you can see that it's propagated for 20,000 days, about 65 years. And the curve repeats itself after 19,000 days. This is the time period that a geostationary orbit takes to complete the precision that you see here. So if the precision has started in 2021, it would take 65 years to complete that complete precision. And yes, all right. For the final thing, so this is a list of all these satellites that are present in the geostationary orbit, plotted with inclination with respect to run. And as you can expect, or as one expects, the active satellites would need to have the inclination exactly 0 for them to work or do the respective function that they are intended to do. So all the active satellites are placed on 0 inclination on the x-axis. But as soon as you lose the active status, so the satellites which are not controlled anymore, they start the precision orbit. They start doing the precision that we've seen in the previous slide. So the precision has a maximum inclination of about 15 degrees. So you see these unique or identifying or the curves that stand out that many satellites are undergoing, right? So if you see here on the right side, that would be the satellites that were first released, or in the early ages of space launch, in the early ages of space launch, so about 60 years or years ago, so they're finishing their orbit. And these ones on the left side of the curve are the satellites that are recently released from active status. So it's very interesting to see how different satellites are, whether based on looking at this curve, if they're active or not, or how long ago they were released from the active status. And yes, yes. So if you have any questions, we can talk about them now.
Yeah, thanks so much, Chaitanya. That was a great presentation. We do have a couple of questions for you. The first is, how did you and the students that you work with learn to use FreeFlyer to do this project?
Sorry, didn't get the second part. Could you please repeat, Mark?
Yeah, how did you and the students that you work with learn to use FreeFlyer and apply it to this project?
The documentation is very helpful. The documentation was so initially the university, there is separate segment of documentation for university students. That was helpful, but for this particular project, we were going through the documentation and looked at the resources that they have on YouTube. And if for few questions, we can also ask for the help desks. If you send an email, they'll respond very quickly.
Awesome. Next one is, have you considered how to incorporate weather models or weather information into prediction of future opportunities for optical satellite observations?
Oh, that's interesting. We haven't considered that. We've relied on predictions, which actually delayed our observations a few times because the weather was not that accurate as we imagined it to be. But that would be very helpful to consider as well.
Sure, and I'd like to add that we're tracking that enhancement in FreeFlyer. It's not necessarily on the roadmap for the next release, but if anyone else is interested in that type of capability or has expertise in it, we'd love to incorporate that into FreeFlyer. So definitely a good question there.
Yes.
Next is, how do you decide which satellites to take observations of?
We decided based on, so it's a university exercise, so we decided based on how bright the satellites are, how reflective their surfaces are. So the Celestrak has a list of the 100 brightest satellites that are currently revolving around Earth, and we chose that list. And apart from that, there were a few interesting constellations that we wanted to look like the SpaceX constellation. We also wanted to, so we combined those both, for utility and also for interest.
Okay, great. And then the next, there's a couple comments from some of the developers of FreeFlyer, but if you tuned in yesterday to Dave Conkey's presentation on SGP4 versus SGP4 XP, Dave was saying that it might be of interest to you to use the SGP4 XP propagator. It could be a little bit more accurate. It could help you, more accurately get observation data for those satellites for your optical telescopes. So definitely check that out. We'd be happy to work with you to get that set up in your current mission plans.
Absolutely, that would be helpful to improve the accuracy to make it more reliable. That would be very helpful. I would say thank you.
Yeah, and also regarding your comment on the formatting of FreeFlyer's output for your antenna, we think that's doable in the report interface. You can fully customize the output of FreeFlyer, so we think that we can take that format that you require for your telescope and natively output that from FreeFlyer pretty easily. So again, we'll get in contact with you and help you work through that problem.
Right, thank you. To finish, are there any other questions, Mark?
That's it.
All right. So to finish, I'm going to share this presentation on LinkedIn. I'm a great believer of sharing. So you can also find the videos that I've seen on YouTube channels or GitHub and the codes on GitHub. If anyone is interested, we can use that. You can use that. Thank you for the opportunity, Mark.
Yeah, thanks so much for talking with us. It was a great presentation. We love hearing how university students are using the FreeFlyer software. So yeah, thanks again.